In this week's video, we will be discussing two topics about energy. First, we will do a problem of lattice energy, and then follow that with bond enthalpy. The first problem we will do this week is our lattice energy. So order the following ionic compounds in increasing lattice energy: copper chloride, cesium bromide, iron oxide, nickel oxide, palladium sulfide, and strontium iodide. So where do we begin? The first thing you will want to do is think about the ideas of Coulomb's law. Coulomb's law said that the lattice energy is equal to a constant times R2 charges over the radius. But while we don't use the math, we can take two important general ideas from that equation. The first important idea is we want to look for large charge difference, because it will have a greater pull towards the atoms and we will get a higher lattice energy. So what we're going to want to do is organize and determine who has the largest charge difference. First species we're going to want to start with is our copper chloride. Chlorine is a halogen, so we know that it will typically form a -1 charge on the chlorides. Because there are two, that means that the copper must be 2+. Notice that it has a difference of 2+ to -1. Now we can go to our cesium bromide. Bromine is in the same group as chlorine, so it will be -1. That means that the cesium must be +1. So now we have a +1, -1 difference. If I go to the iron 3 oxide, our oxygen is in our column of 6A, so it's going to be -2. This means that each iron must be 3+, so that way all of the charges will cancel. Notice that this has a very large charge difference. Now I can go to my nickel oxide. Oxygen again is -2, and seeing that there's only one nickel, it must be 2+. Finally, we'll go to the palladium sulfide. Sulfur is in the same column as our oxygen, so it will be -2. Therefore, our palladium must be +2 as well. So our nickel oxide and our palladium sulfide have the same charge difference. Our last example, our strontium iodide. Iodide is in our halogen column. It is -1. There are two of them, so our strontium must be +2. Our biggest example here is our cesium bromide, which is +1, -1. This has the lowest charge difference. That means it will have the smallest numerator in our Coulomb's law, therefore giving us the lowest energy. So which one's our highest difference? You will notice that that is the iron 3 oxide, because it is +3 -2, which is a greater charge difference than anyone in the group. That must give us the biggest numerator and our largest lattice energy. Now you'll notice that we have two pairs that are very similar. How do we break the tie? Well, that's done using the radius. So our second thing that we must do in order to break the ties of our large charge difference portion is we must look for the smaller radii to break our ties. So now what we can do is we will group the two pairs together and compare only species that have the same charge difference. So we will do that with our copper chloride and compare that to our strontium iodide. That we can also compare our nickel oxide and our palladium sulfide. This is going to go back and use a chapter 3 idea of atomic radii. So let us look at the first pair. When doing this, you will see that strontium iodide is both larger for both atoms. The strontium is bigger than the copper, and iodide is much bigger than the chlorine due to its position in the halogens being lower. So if both ions are big, this means that we're going to have a large radius and a lower lattice energy. That means that our copper chloride is going to be the stronger lattice energy. What about our other pair? Is it obvious to you which one should be bigger? In this case, it's going to be our palladium sulfide. Palladium is larger than nickel due to its location in the transition metals and farther down in a column. And sulfide is larger than oxygen, being directly below it. This means that our nickel oxide is going to have a stronger lattice energy. So now that we've broken the ties, we can start to organize this in our order. The lowest lattice energy is still going to be our cesium bromide. That was determined using our Rule 1. Now we must go and try to break ties in our +2, -1 group. Well, we did that using Rule 2. Because both ions were very big, our strontium iodide is going to be next. Immediately following that will be our copper chloride. Now that we're halfway there, we have to break the other set of ties, and that is our +2, -2 group. We know that because the palladium sulfide, both ions are big, it's going to be the next one in line. So palladium sulfide is going to be the fourth in our group, followed immediately by our nickel oxide. The last one in our group is going to have the highest charge difference. This was determined in our first rule, and that is going to be our iron 3 oxide. You will always use the large charge difference to determine the original order. You only use the radii to break our ties. In our second problem, using bond enthalpies, approximate the delta H for the following reaction. This is HCN plus 2 hydrogen molecules, giving us CH3NH2. When starting this problem, the first thing that you need to do is draw the Lewis structures. So we will go through our order of drawing Lewis structures before we go to bond enthalpies. First, we must draw the skeleton structure of HCN. This has a total of 10 valence electrons, 1 from hydrogen, 4 from carbon, and 5 from the nitrogen. Once we've done this, we must take our valence electrons and put them around the most electronegative atoms. This is done by putting them on the nitrogen. Carbon does not have its octet, so now I must move 2 lone pairs from the nitrogen to form a triple bond. This will give us the correct Lewis structure for our cyanide. This is hydrogen cyanide, and so now you will get H bound to a carbon, which is triply bound to a nitrogen that has a lone pair. Our 2 hydrogen molecules are just hydrogen atoms bound to each other. This is one of the most simple bonds that we have in chemistry. Now as we are going to form our final compound, which is called methylamine, we must figure out how it is all connected. The best way to do this is start with our carbon in the middle. What we will need to do is put that carbon and make sure that we handle it appropriately. You will notice that it has 14 total electrons for our valence of all of our atoms. So now I will take 3 hydrogens and bind them to the carbon. Now we will take that carbon and bind it to the nitrogen. Remember that hydrogen does not want to have more than one bond. We will now bind the last 2 hydrogens to the nitrogen, and we will have our methylamine. But notice we only have used 12 electrons. Where do the last 2 go? The only species that is not fully with its octet is going to be our nitrogen. So counting up all 12 electrons, you will notice that I am only 2 short from having a complete molecule. Putting those 2 electrons on the nitrogen now gives us our 14, and you can see by the counting that I have 14 used electrons. That is a good Lewis structure. So I've used all my Lewis structures, and now what I need to do is itemize what bonds are in what molecule. This will help us pick out the correct bond enthalpies for the various species. In our hydrogen cyanide, I have one hydrogen-carbon single bond. And I also have one carbon-nitrogen triple bond. We must make sure that we select the correct energy for that bond. For the hydrogen molecules, we have two of the hydrogen-hydrogen single bonds. Notice that even though we have two molecules, they use the same type of bond. We can itemize them together. For our methylamine, we will have three hydrogen-carbon single bonds. This is equivalent to the hydrogen-carbon single bond of our hydrogen cyanide. We have one carbon-nitrogen single bond. Notice that this is different than our carbon-nitrogen triple bond of the other molecule. And finally, we have two nitrogen-hydrogen single bonds. Now what we would do is go to our textbook and find the various energies of all of these bonds. You would be provided this information on an exam, or a chart will be given to you in ALEKS. The first one that we would like to give you the energy of is the hydrogen-carbon single bond. This is 413 kilojoules per mole. We want to put that value for both our product and our reactant molecule because it is the same type of bond. The next we will give you is our hydrogen-hydrogen bond, which is 432 kilojoules per mole. If I go to the nitrogen-hydrogen bond, that is a value of 391 kilojoules per mole. Now we have to discriminate between our single bond and our triple bond. Remember that our single bonds should be weaker, so it should have a lower energy. That value is 305 kilojoules per mole. For our triple bond, that value is 891 kilojoules per mole. Remember, having a multiple bond makes it shorter and stronger. That's produced by having a higher energy. So now that I have all the individual energies, I must go put it into my equation. The delta H of a reaction is equal to the sum of the bonds broken. Bonds broken means that it is all of our reactant bonds. So that's all of our energy from the species on our left. We are going to subtract that with our sum of the bonds formed. These are all of the bonds of our product molecule. So that is going to be everything here on the right. Now that we have everything listed, we just must make sure that we do the correct addition and subtraction when organizing all of these molecules. We must add the 413 of our hydrogen-carbon single bond plus the 891 from our carbon-nitrogen triple bond plus 2 times our 432 kilojoules for our two hydrogens. That is the sum of our species in the reactants. Minus our 3 times our 413 for our hydrogen-carbon single bonds. We must add that to the carbon-nitrogen single bond at 305. And finally, we will then add it to 2 times 391 for our two NH bonds. If we sum up all of our bonds broken, we should get a value of 2,168 kilojoules. All of our products summed together are 2,326 kilojoules. So now we must take the difference of those two values. If we do that, we will get a value of negative 158 kilojoules. So if we were to run this reaction with an entire mole of our HCN with 2 moles of H2 and get 1 mole of methylamine, we would release 158 kilojoules per that mole. As you've seen in this video, handling ionic compounds and covalent compounds are slightly different.